we end up being 2 orders of magnitude faster across basically everything. So you can expect something that takes 5 hours in cargo-mutants to take 18 seconds with mutest-rs.
Yeah, the next talk is by Zalan Vai, and yeah, they joined us from Sheffield doing his PhD there, and I think I will hand over the word to you and have a great time.
Hello. Hopefully everyone can hear me online too. But yeah, I'm Zalan. I'm a PhD student in mutation testing at the University of Sheffield. And I work at the testing research group within the university. I'm the creator and developer of mutest-rs and have been for over 4 years now. That's when the project started. And that is a mutation testing tool for Rust programs, which is effectively what I'm presenting today. I'm also a member of the Safety Critical Rust Consortium, specifically the tooling subcommittee, and I was invited on to the Safety Critical Rust Consortium recently because of my work on mutation testing, and that, of course, has many ways in which it's applicable to, amongst many other things, safety critical programming. So what you can see, what I'm presenting today is available online at mutest-rs. So if at any point you're interested in checking it out, please do. Before we get into what mutation testing is, I just sort of wanted to show that it is actually being used across the industry. So Google and Meta both employ an admittedly limited form, but still a form of mutation testing. And they apply that as part of their continuous integration on their famously massive repositories. Of course, anyone who wants peace of mind over their tests may look to using mutation testing as a technique for that. So if you've ever asked the question, have I tested enough? Or maybe there is more left to do, then mutation testing can, if not give you, nothing can give you an outright yes or no answer, but it can certainly give you direction in terms of where to test more. And as I alluded to earlier, mutation testing and some forms of it is actually required for some safety critical certifications. So again, anyone who is in that field, if for example, you're working towards an ISO 26262 certification or some of the IEC standards, at some point you'll have to look towards some form of mutation testing. So what our tests do not catch can be quite surprising. When we find a bug in some well-tested code, it can really catch us off guard. Sometimes we simply do not think to thoroughly test all of the code paths that exist in the program and look at all of the edge cases and simply focus on the happy path. At other times, the code simply changes. It evolves over time. It gains new options, new code paths. And so with that, the code changes and the edge cases change too. Yeah, as software grows more complex, this is particularly the case. And so the tests were perfectly fine before, but as it was extended, as it was improved upon, hopefully, then the checks that existed before are suddenly not enough. It's very much a scenario where sometimes, testing still lets bugs through. However, it stands to reason that we could actually write tests that are strong enough to actually catch a lot of these issues out. And so it would be really nice to have some sort of process, some sort of technique, have the insights in place to figure out where we should be going with our testing. So to improve our testing and with it our chances of catching bugs, we ultimately have to figure out what behaviors of the program our tests do not cover. So in that typical testing scenario on the right, we can see, we run the tests against the program to check it. And as part of that, the test looks at the checked behaviors. That's what the tests capture. But there's also unchecked behaviors in the program that our tests simply do not at the moment. And for testing to really be successful, you need two things. You, of course, need to capture the requirements, what you want the system to do, and hopefully you know that in great detail. But in addition to that, the tests also have to fail if the program happens to be incorrect. And so this is ultimately what gives tests their strength. Without that strength, those unchecked aspects of the program that I've alluded to previously can simply exist. And whether they're correct now or even they're incorrect now, our tests simply won't tell us. And so anything that happens to those unchecked parts of the program, again, they could contain bugs now, or they can grow to contain bugs in the future. So what if we inverted the process of the typical testing scenario and instead used programs against our tests? Specifically, we want to answer the question, given various program behaviors, which are different from what we're normally testing, which ones do our tests allow through, and which ones do they successfully catch out? It's this ability of tests to differentiate between correct and incorrect that we are really trying to evaluate. And so since we already know that hopefully the program that we have is mostly correct, we're under that assumption because all of our tests currently pass and we're reasonably happy with what it's doing at the moment. How about we use the program, the original one, to derive faulty ones? So basically, we're introducing small little changes that are specifically trying to be bugs in the program and see how our testing fares against that. So this is the process known as mutation testing. And specifically, the mutation part, the reason it's called mutation testing is mutations refer to those intentional changes that we add to the program that result in the faulty behaviors. And in effect, we're creating hypothetical program test cases for our tests. So there's a bunch of use cases for mutation testing. Of course, the first one is improving the testing strength. But on top of that, sometimes throughout the process of mutation testing, you actually find that maybe the mutated code is the correct one, and what you've had there was incorrect all along. And again, your tests were not telling you about it either way. And so it's actually sometimes possible that you find bugs through the process of looking at these mutations and seeing the ones that were not detected by the tests. In a similar way, you can find gaps in your requirements. So if you have tests that sort of captured everything that your written requirements had, and yet despite that, you still had this ambiguity that mutation testing revealed, then you may not just be adjusting your testing, but potentially that could raise some discussion around the requirements too. So, of course, in general, you can evaluate the testing quality. Another interesting use case is you can use mutation testing not just on your own code, but on the code of others just as easily. So you can, for example, use it to evaluate dependencies. This is, again, especially important in some more controlled environments, for example, safety-critical environments, where every single decision around which dependencies to use or not use involves quite a lot of process, rightfully so. You're taking in code that is not developed by your own team, and that involves risks. But with mutation testing, you can sort of gain an insight into how good their testing is, which of course is a really good indicator of how good the general code itself is. And again, as I mentioned before, mutation testing can in fact be used as part of some software qualification processes, which is very important. And on the theme of today's session, you can also use mutation testing in an agentic loop, and you can use it as more additional feedback in some kind of loop. So it can be as simple as if your agentic loop contains a requirement to run cargo test and make sure that all tests are still passing, then you can replace that with mutation testing instead, because that runs your tests, but also it runs all of these mutated programs on top. And we'll look into what these look like as well to really get an idea of what mutation testing is about. But you might be asking, doesn't coverage already do this? And it's a reasonable question. But ultimately, here we've got an example. This is taken from the Alacritty code base, but it can happen anywhere. And here we've got a function that is loading some configuration options, and this is code that is entirely covered. It has achieved 100% coverage by the test, so it has line coverage. And we can see that despite that coverage existing, we've got a change on line 102, where we're turning the bitwise assignment operator, the bitwise OR operation into a bitwise AND. And again, this is a kind of mistake that's actually quite typical, especially, for example, with bitwise operations. It can be quite tricky to wrap your head around the exact right set of operators you need. You can start building truth tables and such to figure out exactly what you need, but it can be tricky. And as it turns out, making that change, which of course changes the behavior of the program, changes how these configuration options are handled quite significantly, is entirely undetected by any of the tests in Alacritty's code base in this case. Yet they had 100% coverage. So clearly there's a bunch of things that coverage misses. In fact, coverage only really tells you the places that completely lack tests. So any kind of uncovered code, of course, is not being exercised by your tests. But just because something is covered, that only really means that it's been executed during testing. It doesn't really tell you whether the computations that happened along the way were actually properly checked for. So here we have a couple of examples of the mutations that exist in my project, mutest-rs, but some of it also exists in other mutation testing tools, of course. So for example, here we have the Boolean expression negation operator. And to understand how these work, when we talk about mutation operators in mutation testing, what we mean is basically some kind of rule that takes some existing pattern, like a pattern of existing code, and maps it onto some mutated code that has, hopefully different behavior. So in this case, we have some conditional check that is being reverted, so just simply negating that Boolean expression within that line on line 226. And again, that was completely undetected by the tests. So this is a function that is actively used by the test cases, and yet they were not able to detect that some core logic in there was changed. We're able to change relational operators. So we can, in this case, we're just taking away the equality from that greater than or equals comparison. But we can also invert those relational comparisons. And of course, this sort of raises an interesting question of, I think we've all been there. In this case, it's some code dealing with like ranges of possible values that we are categorizing in different ways. And sort of those boundary cases, those edge cases, are always sort of the trickiest thing to wrap your head around. Of course, we can change ands to ors and vice versa. And again, we can do this in any kind of, sometimes this can be part of some very complex Boolean expression. And again, actually testing, checking by sort of doing the opposite, the thing that we're not supposed to be doing, can reveal a lot. So again, these are all undetected mutations by otherwise incredibly well-tested programs that exist in open source Rust. Then we have all kinds of math operator swaps, and there's sort of a long list of them. In this case, we've got a mutation in chrono, which is one of the biggest datetime libraries for Rust. And as it turns out, for example, if you look at the add implementation for time values, or these naive time values, which are not associated with a time zone, then some aspects of that calculation are not actually fully captured by the test cases, it seems. And for example, you can turn the at the top, obviously correct calculation of like converting hours to minutes to seconds. You can actually mess that up, and the tests still don't tell you about it. This one can produce quite interesting and funny results sometimes. As you might imagine, if you have some complex big looping structure and you just start changing the various continues to breaks or vice versa, you can get some very, very subtle bugs introduced into the program. But again, it shouldn't be possible to change them. There's like a very, the behavior there should be very distinct. Then we get onto some of the more complicated ones. We have arg-default shadow, which basically the goal with this mutation is to see if you've actually even tested the various arguments to your functions that you're testing. So in this case, we're able to override the value that is given to a function by just shadowing the name that exists under. So in this case, whatever value you give to the new function, whatever date time value you give it, within the body of the function, the mutation is just going to replace that value with a default value for that type. And again, sometimes you find out that these mutations are not detected, and therefore, you've got some code paths, you've got some arguments that you should be testing. We've also got a call deletion, and this basically takes some kind of function that was originally in the program, some kind of function call, and just replaces it with a default value. So this also works for anything that might have a return value. But you can imagine if you're trying to evaluate side effects, like you're building up a vec over time over a bunch of statements, and you have vec pushes, for example, then this operator can take out one of them. And if that is not detected by your testing, then again, something's clearly wrong. And then we have a very subtle version of that, a sort of variant called value default shadow. Of course, these names roll off the tongue, I know. But they're, of course, describing some very intricate interactions, very intricate changes to the program. It's similar to the previous one, but you see that we're not entirely replacing the function call. We're still running it, so we're still running the memtake function. But instead of giving back the call site, the return value, we're sort of just silently discarding it and replacing it with a default value. So in effect, what we're evaluating here is, are you just evaluating functions for their side effects, or are you also properly testing the values that they give you back as a result? That way we can sort of differentiate between the two. So I wanted to show you a practical workflow with mutation testing, and I think this is highly applicable to agentic use cases as well. So with mutest-rs, with my project, it was basically, the idea is it's as simple to run mutation testing as if you were running cargo test itself. You could just run cargo-mutest run instead. And in this case, we're giving it the --inspect flag. that brings you, like once the analysis is done, it like gives you a nice interface to look at all of the results later on, which I'll show you. So the first step, of course, is to just run mutation testing. And then, of course, you get a lot of results all at once for your entire program. But first, of course, you should be focusing on the undetected mutations, so those cases where your tests were not actually able to differentiate. They were not able to tell that we've introduced all these bugs. And you want to look at critical files, critical functions. Of course, you know your code base best. And with every single project, some parts of the code base are more important than others overall. And within that, you want to potentially look for functions where there are many detected mutations, but a couple of undetected ones. So that tends to tell you that those undetected mutations tend to be a little bit more valuable because those tend to correspond better to these missed edge cases in your testing. So that's usually an indicator that you've got like a function or some part of the program that is relatively well tested, but there's still a couple of improvements you can make. And then you consider the tests that could reach the mutation but did not detect it. So beyond just looking at the undetected mutation, with mutest, you can also look at the exact test cases that were at all relevant to the mutation. And that way, if you start inspecting those test cases and how they relate to the mutation, then that can give you a lot of information as to why your existing tests were not able to detect it. And that can help you figure out specific ways in which you can adapt your test cases and improve them further. And so there's a couple of outcomes here for any individual mutation. Option one is that you discover that there's just no existing test cases that cover that section of code, in which case you get to write test cases. Option two is that you have existing test cases, but they didn't specifically cover that edge case, in which case you can take your existing edge cases, add some additional assertions to it, some additional piece of input data, and you should be good to go. Option three is that of course, your existing test cases did not cover the edge case, but also that the mutated code is actually the correct behavior. And as it turns out, you've had a fault all along. All that to say is that when you're faced with these undetected mutations, you're not just questioning your test cases, but you could also reasonably questioning the code itself. And you can sort of see the original and the mutated version side by side and actually decide which of the two behaviors is the one that you want, the one that meets your requirements better. And finally, as you constantly improve the behavior of the program and the tests, of course, you can run a partial analysis later on. So if you're, for example, changing just one particular file all the time, you cannot be dealing with the entire project all at once. Then there's a handy flag called filter mutations, where you can sort of specify exactly where you want mutations to be introduced. So you don't have to run the entire process again from scratch. You can do partial analysis like that. Because ultimately, this is all a big iterative process. And you're going to be running mutation testing a couple of times over and over again, just like with any other tool, to check that your improvement work is going well. So because we're unpacking and exploring the various unchecked behaviors that exist in the program, in this process, we're bound to find not just testing gaps, but also find things about our programs, like untested parts of the program, including those existing bugs. So again, as I mentioned earlier, a lot of the times mutation testing can sort of bring your attention to these edge cases. We've seen this example before. And again, you sort of have not just a question of what should the test be doing, but also you can start questioning what should the program be doing. And you will have probably heard of property-based testing, especially in the Rust community, is an incredibly important kind of testing, and one that's shown time and time again to be very, very effective and powerful. And so it's really good at testing complex logic. But of course, it's a tool, and it's a tool that you have to use well, and you have to use it properly. And as part of mutation testing, we found that property-based tests are in fact quite effective, which is good for all of us to know that property-based tests do in fact hold up quite well. But at the same time, we have actually found examples in incredibly well-tested open source Rust libraries that have made extensive use of property-based testing, where we've still found testing gaps that were directly related to the property-based testing that they were doing. And so in this example, sort of just to explain what's going on, we see what mutest-rs calls a trace, in which at the top you have a property-based test defined. In this case, it's done through quick check. So you can see it's a parametric test case. It's the property-based testing framework is actually able to pass in values and repeatedly call this test case. And it's sort of trying to guide the testing into a particular direction. And then later on, at the bottom at line 1283, we can see within the assertion itself a way in which the property-based test case is able to reach into a particular program function. So that's sort of the place at which the test actually invokes the function. And at the bottom, you can see that it's a function that we've introduced a mutation into. It may be a little bit difficult to read from far away. But in this case, all this mutation is doing is replacing the first part of the comparison with just a default value. So effectively, it's entirely killing what is supposed to be an equality implementation between two types. And again, of course, it's just one part of the overall property-based test case, but it was not detected still. So to move on to mutest-rs itself, how mutest-rs works, and sort of some of the interesting aspects of that. The mutest-rs is based on the compiler itself to achieve mutation testing, and I'll get into exactly what that means and how it works later. So at its simplest, if you wanted to implement mutation testing, what you could do is just make copies of the source code, make the actual changes to them one by one, compile that source code, this modified source code, run the tests on it, and see what the outcome is. And you could repeat that over and over again for every single mutation. But as you might imagine, that can get very expensive very quickly. And when we're talking about mutation testing, we're talking about hundreds or even thousands of mutations at a time, even for like medium-sized projects, for open source Rust libraries, which a lot of them are not typically that big. And so that can really add up. So instead, let's do something a little bit smarter. To generate the mutations, first, instead of generating anything at the beginning, we're able to just check which parts of the program are actually being exercised by the tests. As it turns out, commonly, you're not exercising the full extent of your program. And so seeing that can be quite helpful. And then within the parts of the program that you do exercise, what we can do is just apply these operators that we've talked about previously, the ones that map some original piece of syntax to its replacement, to its mutated counterpart. And we apply them into every single possible place within those functions that we can. So every single syntax node. Once we've generated these mutations, and again, we've not written them so far anywhere, it's just we've got this in-memory representation of them. Once we have that, we can start embedding them into a single program and compile it once and run this mutant program to evaluate the mutations. And to do that, for each of the mutations involved, you can enable it one by one, enable the corresponding code path, the corresponding changed code, and also, of course, run the relevant test cases for it. And we know what the relevant test cases are because of step 1.1. We've checked the relationship between the various parts of the program and the various test cases, and we actually know the exact set of program functions that are being run by the individual test cases. To see what an operator looks like, and this is something you could do yourself as well, and this is very much a design goal with mutest-rs. So this is how the built-in operators look like. But of course, if you had something specific you wanted to implement, you could do that yourself, and it's just Rust code like anything else. So this is roughly how the built-in Boolean expression negation operator is implemented. So you just declare a type, and that can, in this case, is just a unit type. But if you wanted to include configuration options on it or anything like that, you could, and just have fields for that. And we're implementing the operator trait, which comes from mutest-rs, of course. And this operator trait has a single function, try apply. As the argument, you get the mutation context, which, as you can see from here, it gives you a bunch of information. It tells you where the operator, where mutest-rs is attempting to apply the operator to. But it also gives you access through that tcx variable. It gives you access to the compiler. Basically, all of the analysis that the Rust compiler typically does on a program, you can do within the context of these mutation operators. And we'll see how that looks like in a little bit. And of course, you're given this context, but as a return type, you're able to optionally create mutations with this operator. And so the job of such a function is twofold. You can determine where you're able to apply the operator to, and also how exactly that looks like. So we're just looking at, in this case, we're looking at any sort of expression that exists in a function body. And if we're being applied to anywhere else, we just return none. And in this case, this is the couple lines of code that interact with the compiler. So in this case, we're asking, like right here, we're asking the compiler to type check the body of the function that we're currently trying to introduce mutations into. And most of these are cached operations, so they go by quite quickly. And then we're able to, from that analysis, specifically ask for the type of a particular expression. And so we grab that, and then we can easily determine whether the expression we're dealing with is actually Boolean typed or not. And in this case, because we only want to deal with Boolean expressions, we're able to ignore anything that is not a Boolean typed expression. But if it does happen to be a Boolean typed expression, then we can simply create the corresponding syntax tree nodes to add the negation on top of the existing Boolean expression and sort of package it up appropriately how mutest expects it to look like into a logical mutation into the program. And those can contain the actual changes that you make. In mutest are called substitutions. For example, what this is saying is that we're replacing the original expression node with an expression that is the negated version of it. But as you might be able to tell, we're actually able to add a bunch more substitutions. So mutation could be made up of multiple changes at the same time. And so to actually get all the mutations into one program, this is sort of what the generated code looks like. And this is something you do not interact with in the slightest. But I thought it was sort of interesting to see how it works under the hood. We're able to generate conditionally branching code to embed all of the mutations into a single program. And you can see that for this original piece of code, which in this case comes from hash brown. So this is an actual piece of mutated code, not something made up. We can see how certain branches that are being taken correspond to either the default version, the one that exists in the program, or to the various mutated counterparts. And we're able to change that with this generated, essentially a specific lookup table that gets generated along with these conditionally branching expressions that basically act as a massive switchboard that allows you to change which code paths are being taken at every single one of these locations at runtime. And of course, for this to work, all of the mutations we generate must pass the various compiler checks. So of course, the one sort of downside of trying to do it so efficiently is that if you do happen to generate, if you have a bug in mutest-rs or in the operators, and you generate something incorrect, then the compiler will reject everything. So one mutation can, in fact, take down the entire process. But of course, all of those are bugs, and all of those are things you can and we have worked through over time, and they happen to be few and far between. And yeah, each of those code paths can be toggled on and off at runtime. There's also a whole aspect of how do we do this safely in Rust programs. So as it turns out, because we have access to this distinction of safe and unsafe operations, that actually turns out to be incredibly useful for mutation testing purposes, for example. So of course, we probably know about what unsafe is in Rust. In a nutshell, it's any kind of code section where the compiler's proofs, the compiler's static analysis, is not sufficient. And so instead of relying on the compiler telling us what is being wrong, hopefully as the actual developers, we've done our due diligence to write correct unsafe code. So that even though the compiler cannot tell us that the code is correct, we know that we've done the right things to abide by what unsafe code should be doing. Now, of course, if we start mutating this kind of code, it becomes incredibly easy to break those hand-enforced safety contracts. And of course, the result is undefined behavior, not something we would like. So ultimately, there's a case for separating out safe and unsafe mutations. And as it turns out, that with the right analysis in place, if we designate any kind of code that is surrounding unsafe code, again, that could sort of feed values into the unsafe code section in some ways that are undesired, or also any code that is being called by unsafe sections. If we designate those as unsafe mutations, and of course anything in the unsafe block directly as well, then actually we can perfectly separate the two classes of mutations. And why that is useful is, of course, it's still important to look at the unsafe mutations, but we can execute them in a different way, in which case the undefined behavior aspects of the program are less important, less impactful. You can run it in a separate process, for example, separated from everything else, or in some sandbox, and it's not going to affect the rest of your evaluation. So here we've got a simple example of an unsafe mutation. Again, that's a mutation that's not affecting the unsafe code directly, but by changing the buffer size from a fixed 1024 bytes down to just a 0, and then the later on fixed lookup into this buffer, of course fails with the now new version. And it unfortunately fails because it's an unsafe, unchecked lookup. It could be reading garbage memory. It could be the process could be evicted by the operating system. You effectively don't know. So with all of this in mind, how fast is it to actually run mutest-rs? And I think the best way to show you this is just to show it on a bunch of programs. So here we've got Alacritty. This is, of course, not the entirety of the Alacritty code base. This is a particular crate in Alacritty. This is like the main binary crate. And so we can see that that's why sort of the lower test count is there. They do have a lot more tests, of course, across the entire project. But we've got around 80 tests. And for this code, we're able to generate just under 2,000 mutations. And so this first one is sort of the worst case scenario for mutest. This is when you specifically request it to run every single mutation, every single test case in its own process, separate from everything else. As you might imagine, if you just multiply the two numbers together, that's the number of process invocations you endure, and there's a massive overhead there. This is definitely the worst case scenario. And even with that in mind, from end to end, so that's from running mutest-rs to getting your results, including the generation of the mutations and the programs, that runs in just over a minute. But also, if we run it by default, where everything is run on threads, that just takes just under 12 seconds. And with some of the work that I've been doing, you're able to halve that on top and just get to 6 seconds instead. And we're getting to the territory where this doesn't actually take significantly longer than just running the test suite by itself. We have Rustls, the main Rust TLS implementation. So that has a couple more test cases. In this case, roughly a similar amount of mutations. And again, we can see that we are feasibly doing mutation testing in less than 20 seconds. And lastly, sort of a really, really big example. This is Gleam core. Gleam is a language compiler written in Rust. It's implementing its own language. But we can see a big jump in the number of test cases and also a jump in the number of mutations. And this actually captures pretty much the entire language, including the type checker, including syntactical parsing, and all of those aspects of the Gleam language. And we have a timeout in the process case. Ultimately, it's like I ran it for 20 minutes, and I didn't want to run it anymore. And ultimately, I think that speaks for what we're trying to do here. For this kind of technique to be useful, you want it to be relatively quick. But if we look at the threading case, the default, then we're able to finish in just 2.5 minutes. And with some additional configuration, we can take that down to a little bit more as well. And so suddenly, that's an amount of time that you might actually wait for such results. So if you've ever heard about cargo-mutants, that is a sort of, it's an implementation of mutation testing that represents the simplified version that I discussed before, where they do actually make copies of your source code and compile everything one by one. And of course, it being simple, there are some advantages, just it being a simpler approach. But at the end of the day, compared to cargo-mutants, we're able to get away with a single compilation. We're able to make it so that every generated mutation is valid and reachable, which cargo-mutants has no idea about. So it could be generating mutations in uncovered code. You can express any kind of code mutation you want in mutest-rs. So whatever complexity of mutations you want to be looking at, you can do that. We're not running any kinds of non-relevant test cases, which happens to be a big optimization at runtime. And ultimately, we end up being 2 orders of magnitude faster across basically everything. So you can expect something that takes 5 hours in cargo-mutants to take 18 seconds with mutest-rs, which, as you might imagine, improves the feasibility of mutation testing quite significantly. So mutest-rs is open source, a dual license under the standard Rust licenses. It's available at mutest.rs. It is applicable to any Rust project without any kind of configuration. So if you can run cargo test, you should also be able to run cargo-mutest instead. There is JSON output for any kind of external tooling and also for research purposes or anyone who wants to make downstream tooling based off of the results. And there's also an interactive web-based inspector where you can actually look at the generated mutations. You can break down the exact results that came from it, and you could just run that anytime with cargo-mutants-inspect. As sort of what's coming up with mutest-rs, one exciting piece of work is that we're now, this is not upstream yet, this is something that's coming over the next couple of weeks, but we have working versions of mutest-rs that are able to mutate and then test embedded firmware written in Rust on device. So if you're doing any kind of embedded IoT development, mutest-rs should be applicable in just the same way as it is for regular desktop applications. And in fact, this extends to being able to distribute mutation testing across multiple chips at the same time. So if you connect multiple of these IoT boards to the same machine, it's able to distribute the test amongst them. Of course, many new mutation operators. We currently have a basic set of 18 with a couple of interesting ones. There's a bunch more that we are wanting to add over time. Some specific integration into CI scenarios would be very nice, especially over time, so that, hopefully make it easy for people to keep up mutation testing. We also, this is sort of one of my research areas at the moment, one of many, which is to have a way of having an incremental mutation testing that is aware of version control, so that you can, because individual commits in a version control scenario only change very little of the code, it's actually possible to figure out, to only run a partial analysis of mutation testing and figure out exactly what parts you need to reevaluate and where new mutations might have arisen, where old ones could have died off as the code has changed. And we've got some experimental work there that's actually able to figure this out and makes it so that you have to run very little of the analysis again to get the full result set. Yeah, this is my project that I've been working on for quite a long time. Thank you very much for the invitation. Thank you very much for listening to my talk. You can reach me on all of these channels. There's my personal website at zalanvai.com, and you can check out, again, mutest-rs at mutest.rs. Thank you.
Thank you very much for this amazing talk and your amazing work. Like 2 orders of magnitude is so powerful. Like I was blasted away when we talked at Rust Nation about that, and I'm quite. I think there will be many questions. Yeah, where do we start? So first of all, let me start. My one question. I was quite curious about the mutations testing for unsafe code blocks. So is that also like you can use unsafe in scenarios where you really want to squeeze out a lot of performance? For example, when you use dynamically sized types or stuff like that. And I think another use case where you see unsafe a lot as Rust programmer is the FFI. And I'm just curious, like on those both scenarios, where do you see mutation testing? Can you give an example for that?
So I found that, of course, unsafe code there's not a lot of unsafe code for individual projects, but it is prevalent, right, for performance optimizations. So in some cases, there's a set of subjects that I've been looking at quite a lot throughout my various pieces of research, and about half of them contain some amount of unsafe code. And of course, the majority of that is for the purposes of FFI. I think in the FFI scenarios, the outcomes for unsafe mutations tends to be less interesting. And in the cases where you're trying to use unsafe more for the purpose of performance optimization, or where you're designing some sort of data structure that is specifically, doing all the right things, but it's somehow breaking the fundamental semantics of Rust that it can enforce, that are compiler enforced. Those are the cases where the unsafe mutations tend to be a bit more on the interesting side.
All right, thank you. Yeah. So I see more questions here. Maybe we have a question online?
Hi, Tim. No questions online so far, but also it might partly be because I wasn't sure if I'd be able to take any, so they might have just not asked because I've had to step away. But I could ask a question. A really, really interesting talk. I guess I'd be interested to know, how do you test mutest-rs?
Fantastic question. How do you test the tool that tests your tests? And it's sort of an endless cycle. So at the moment, and it's actually quite a tricky thing to test. At the moment, a lot of the testing of mutest is inspired by the compiler's own testing. So the compiler, beyond a couple of unit test cases that are thrown around, actually doesn't make a lot of uses of unit testing, partly because you would need to set up a lot of compiler state to be able to actually test things directly like that. So instead, what they tend to do is focus on what can be expressed as input programs. So in a way they call it effectively UI testing, but it's sort of just a more handy way of doing snapshot testing in a way, where they just write individual Rust files with a couple of additional pieces of common-based syntax that tells the harness exactly what kind of things to look out for. And that's basically what mutest-rs is doing as well. So I've built a custom harness that is able to invoke mutest-rs in a bunch of ways. There's a lot of trickery we have to pull off with the compiler. So as you might imagine, the compiler was built for a very specific purpose. It's a linear pipeline going from input source code to generated machine code. And to do what we do, specifically to be able to take the analyzed semantic representation of Rust and also sort of pipe that back and be able to make code changes based on that to then create a mutated version that we can compile again. There's a lot of trickery that we have to do there in the middle to make that happen. And so a lot of the testing, beyond just the end product, of course, of how the individual mutations work out and such, a lot of the testing went into those specific interactions where we're sort of bending the compiler to our will. So the short answer is a lot of testing that the compiler itself would do. We have to do as well.
Very cool. I see 3 questions here, but I'm not sure for the order. Dominic, Henrik, and Lucas. Yeah. I go for Henrik. He's closest.
Hi, I have a bunch of questions because I got from your talk that we should start doing that in my team. But the first one for me would be, we are doing numerical software. So we have large problems with determining what is actually true. So in your less or equal operator example, I thought to myself, I think in 99% of locations in my code base, it doesn't really matter. How can we deal with that when doing mutation testing? That we have things where we know it doesn't really matter.
So, for one, personally, I would say that maybe it should matter, But of course, it very much depends on the kind of logic you want to achieve. Now, of course, if you're dealing with like float-based calculations, then of course, I mean, everything around that gets murky.
Well, we still for
but maybe you still want to consider those interaction points because if for nothing else, for the purposes of like, it's generally beneficial to build programs as much as possible in a way where they're as deterministic as possible, which of course goes against the whole line of agentic programming and such, and how we go about that nowadays. But of course, there's a lot of benefit to creating deterministic programs, trying to stick to that as much as possible. And that includes like making sure that those edge cases are sort of properly handled. With all that said, there are sort of escape hatches. So with mutest, there are actual attributes that you can place into the code, like mutest skip and mutest ignore. You can ignore an entire function and just not put any mutations into it, or you can annotate specific nodes like statements or sub-expressions within that, and say explicitly that you do not want to introduce mutations there. So there are escape hatches. Of course, there are some valid cases where you might want to do that. That is the solution that we have at the moment. Of course, I can see how that can become tedious, annotating everything like that. I'm essentially waiting for feedback in practice to see if maybe there is some better solution that we could come up with there. But I feel like I essentially need to wait for people to start making use of that at scale and encounter those issues of like, okay, this works, but we have to do this 100 times and is kind of really tedious, but for our use case, we could do something a little bit simpler than that. How about we incorporate that into mutest-rs? So I'm very much open to any kind of feedback like that.
Yeah. Awesome, thank you very much. Because versions often is something zero after a billion floating point operations. Questions like that.
Thank you. Yeah, thanks for your talk. You were talking at some point about testing data structures, and some of the more complicated data structures to build are often the concurrent ones.
Yes.
And so some of the comments you made on property testing made me think of how concurrent data structures are sometimes tested. I'm assuming you know of the Loom tooling for kind of running through all concurrent operations. So something that I think could be incredibly useful, for example, would be testing, okay, does the data structure still work if I replace the consistency, like, what's it called? Like how consistent the atomic operations are, for example, right? But then you kind of need the integration of, I want the mutation, but then I also want to run all of the permutations of the program. So is that an interaction that has come up before, right? That kind of has the same synergistic effects with like something like quick check, or is it more difficult to kind of test multi-threaded, right, atomic code in this way?
Great question. Now, of course, everything about a multi-threaded environment is just more complicated by nature. There's sort of no way around that. But of course, like with mutest, we're engaging with multi-threading in the first place. So that was sort of one of the big design goals. My research has been focused on coming up with all kinds of techniques to not just be able to run test cases in parallel, but also like mutations at the same time. And that can get quite complicated. But to answer your question, so for a concrete example, we've run Tokyo itself under mutation testing. Now, from memory, I'm not sure if the built-in test suite of Tokyo actually makes use of Loom. I know Loom is like one of the sub-projects of the Tokyo ecosystem, but I'm not entirely sure if their testing by default actually incorporates Loom. But as far as I know, everything about Loom sort of like it works on the regular cargo test environments. They achieve what they do with the by just like essentially generating code around your test case when you're like defining a loom-based test. And so all of that should like work out of the box because mutest will not sort of interact with that directly. It's just invoking the test cases that you do give it. And so under mutest, Loom is still able to do all of its normal stuff. Now, of course, with Loom taking quite a lot of time by itself, of course, if you start multiplying it, then it might be very, very expensive under mutation testing. But all of the filtering that we have in place should be able to minimize the costs as much as possible. I'm very interested in hearing people trying out specific Loom-based tests, though. Yeah.
Do you have mutations currently that are kind of specific to areas like that? Like a mutation that would swap sequentially consistence for acquire release or something?
Not at the moment, but that is actually a really, really good idea for a potential mutation operator. And again, because we have access to everything the compiler knows, it should actually be very easy to implement that as a mutation operator. Effectively a good first issue.
All right, thank you.
But I actually love the idea, and I will probably be evaluating it soon, because one of the things that I wanted to move on sort of in the near future was actually adding, I already have a good list of a bunch of new mutation operators to add that I think would be super valuable. But of course, the best way to see is add it and then evaluate it in the real world, run it against a bunch of projects and see what you get. Yeah, I think it would be super valuable to, if I understand it, what you meant is like change for every single atomic operation, be able to change the ordering argument of that atomic operation from the, was it like 4 or 5 options that exist? Yeah, I'd love to see the results of that, the sort of potential chaos that might cause.
Which doesn't really change in the end.
Yeah, I think it cuts both ways, right? Like, does it get more correct if you make everything sequentially consistent? But also, if you have everything sequentially consistent, can you relax it without regressing the program?
Well, you have to be extremely careful with that because it's hard. Very, very dependent on the CPU architecture that's actually in use. Okay. Pass that on.
And that is actually, since you mentioned that, is actually a good reason why when we wanted to support embedded devices with mutest, we're specifically looking at on-device support because we know, for example, in those atomic cases, the actual underlying chip and architecture behaviors matters a ton. And so even your simulator doesn't necessarily match what your actual chip is doing.
Yeah, thanks for the talk from me as well. I will definitely need to test that out on some of my projects. One rather simple question regarding the reliance on the compiler internals that you mentioned. Is it possible to use it with stable Rust, or does it require nightly?
Unfortunately not. It requires nightly, but that is sort of transparent to the user. So every single version of mutest is pinned to, it's built against a very specific version of like the nightly toolchain, which we progress every so often so that we're able to guarantee you the features of stable Rust with a nightly compiler, which effectively means like bumping the version at least every 2 months or so, but in effect we try and make that more often. And just because the more often we do it, the less changes we have to do reacting to the compiler's own changes itself. So it's not something you have to interact with, but yes, every single version of mutest is built against a specific nightly toolchain, and there's sort of, certainly not in the near future, there's like no way around that for the moment. There are some projects in the like the rustc compiler team, like rustc public, which is trying to accommodate to as many of these external compiler-based tools as possible, their use cases, and sort of create a stable interface that is compatible with multiple compilers at the same time. Now, what mutest-rs does bends the compiler significantly from all of those other tools because all they want to do is extract information, but we want to extract information and feed it back into code generation and recompile. So, there's no official plans yet for rustc public to support all the things that we need. But, I'd love to have that discussion with them and see if they're actually interested in, of course, together taking on that work. But that would be in the long term.
Yeah, most likely, knowing what other open RCs there are waiting for ages, that might take some time. Yeah, but yeah, thanks for the answer. Any more questions?
Yeah, maybe we have some more questions online, because we have Zalan here all the time for the evening. And so I think at least 3 questions online too, right? If there are.
I can't see any questions online currently. And
Okay.
unless it's my internet, but yeah, I can't see any currently.
Okay, then I think we wrap it up. Give Zalan another big handful of applause for. And
Sorry.
yeah.
There is a question.
Oh.
Very good. Go for it.
What are the maximum number of mutation tests you have created so far?
Great question. I mean, in total, if you look at every single subject I've ever run, it runs into the millions. But in terms of the biggest subject, I think at the moment it might be. It's a near tie with Gleam core, which is I've shown in terms of the number of mutations and the regex crate. As it turns out, we've not breached the 10,000 mutation barrier or anything like that. And the main reason for that is because everything in Rust, including the compiler, everything is done crate by crate. And as it turns out, for a bunch of reasons, including to try and improve compile times and to improve compiler parallelism, people try to break their projects up, even really big ones, into a bunch of smaller crates. And that has a bunch of advantages. And with mutation testing, we look at things crate by crate, typically. The only exception to that is integration testing, where we specifically had to do some machinery where integration tests are specifically compiled as their own unit. But then, because we cannot look at both the test cases and the program under the same compiler session, because they exist in two crates separately, we actually do some, again, transparent to the user, but some trickery where we make use of the cargo invocations that we have to first, when we encounter the library that is being tested by integration tests, we generate a version of it, which can be later reused for analysis. And then when we encounter an integration test that corresponds to it, we part way of analyzing that, we are able to do reachability analysis across the crate boundary, but then we take the information we receive from that, bring it back into a new compiler session that then goes back to the tested library to then generate the mutation specific for the integration test and tie everything back together. So there are ways in which we do specifically have things to breach the crate boundary, but there's sort of no reason to do that in the general case. And so to get back to the question, it seems to be a natural sort of upper bound as to how big developers are making their individual crates. And that sort of shows up quite naturally in the number of mutations we tend to generate. Of course, that number can increase significantly once we start adding a couple more operators, especially if everyone starts brainstorming ideas for potential operators and we enable all of them. And then, of course, you can have an explosion of mutations that way.
cool sound. Yeah, very good. I mean, the next step would be like, I don't think you should do it, but when you think about end-to-end tests, people spawn like another process.
That is something I've been looking into how to facilitate. So one of the integration testing scenarios is when you're integration testing a binary output. And so like your integration test is effectively a custom testing harness that is like invoking binaries in that way. You cannot fully automate that, but if there was a way to provide the right set of like escape hatches so that mutest can sort of integrate itself into an entirely custom testing harness, in some cases that would be useful. That is essentially what I would need to mutation test mutest-rs itself. Because of course we have our own entirely custom testing harness that is able to, like, the test cases are individual RS files with a bunch of custom syntax in there. That is sort of what we would need to fully mutation test mutest-rs. So it's something that I don't have a fully working solution for at the moment, but it is something I've been looking into, seeing what would be the best way to do it.
Very cool. So if there are no more questions, I would say give another hands of applause. Yeah.